Okay, so let's say that we want to use several attractor points and not just one, like in this case. Okay, so let's see how this thing can be done. Of course, we will have to change the amount of points in this point container, but also we will have to deal with the first, let's say, problems with data manipulation. Okay, so let's say I want to use this new point container and tell this point container I want to set multiple points. So I want just 1 point here and 1 point here. Okay, and therefore I want to use this container instead of this one. Well, I could also plug a cable from this to this in order for this container to receive its contents by from this new container here. But I prefer to Control Shift and drag these two wires here from the old point container to the new one. Okay, and so I delete the old one, and this is what happens. Okay, so you see that there are some problems in this definition because of course Grasshopper is using now 2 attractor points. As you can see, I can move it around 1 and 2, but only the second one seems to work like the previous, let's say, spider, walking spider. Okay, and let's try to understand why this is happening. What is happening here is that the problem is with this component here, distance component, and also with the line component. Okay, so let's see what happens, for example, inside this distance component, and what is coming in from the point A input and point B input are these 2 sets of data. So the first set are the 2 attractor points, while the second set is the whole point cloud coming out from the populate2D component. Okay, so let's say that we want to calculate the distance between these 2 points and these, what is it, 316 points. Okay, how would we do that in real life? Well, we should measure the distance between point 0 and all the points contained into the population here, and then measure the distance between point 1 and all the points inside this population of points. Okay, so this is what we should do in the real life. But what's happening here in Grasshopper is that he's calculating the distance between these 2 lists. Now, Grasshopper, in terms of data interaction inside one single function or component, acts using one main principle, which is called the longest list. If you go into the set toolbar, you will find, for example, in the list group of components that there are 3 functions here at the bottom of this group, which are cross-reference, longest list, and shortest list. So Grasshopper is working with the longest list, and let's try to understand what this criteria looks like in a Grasshopper workflow. So we have these 2 sets of points. Okay, first one contains just 1 and 2 points, and the second one contains a whole bunch of points. When Grasshopper calculates the distance, he is comparing this set with this other set, and what it does is like calculating the distance between point 0 and point 0, and then it switches to point 1 and point 1. So what is happening here is that each attractor point is not interacting with the whole set of population point. Okay, it's just interacting with its pair, basically. So what happens when one list is longer than the other list? This is when the longest list method appears, and Grasshopper, in order to generate a finite number of interaction between couples of data, then what it does is take all the spare data here in the longest list and relate them to the last data available in the shortest list. Okay, so basically what Grasshopper is doing is calculating the distance between the first attractor point, which by the way is this one in the upper left corner, and the first random point in our population, which is exactly this one. Okay, and then it goes to attractor point number 1, which is the second attractor point here, and calculate the distance between all the remaining points except the first point that has already been used and the second attractor point. So this is the first problem that we have here in this definition. And then we also have this thing here, because we have the first 2 points here getting inside the start point of the line component, and also we have the list A. Now the list A is once again a smaller set of points, but we always have one longest list and one shortest list. So the principle is exactly the same. First point interacts with the first point, and then second with second, and second with third, fourth, and fifth, and so on. Okay, so that's why we have one line starting from the first attractor point and reaching the first random point that respects the distance condition in our definition, and then the second attractor point connects with all the remaining points that are close enough to the second attractor point. Now we want to perform an operation which is similar to what we would do in real life scenario, so we must consider the two attractor points separately and not all together, in order to have this workflow happening twice, basically. So let's say that a new user self-taught and without any notion of lists and data tree, what this guy will do will be to maintain the definition like in its working configuration with just one attractor point, and then eventually he would take this bunch of components here, copy paste them, and then tell this one you are a second attractor. Okay, so in this case you will have 2-point container here that you can handle like this, and everything is working just fine, but you have twice the amount of calculation needed for this definition. Okay, so I would not recommend to do this. What I would do is follow our initial instruction to set multiple points here. Okay, and then find a way to consider these attractor points like separately and not in just one single set. This thing here leads us to considering one particular data structure in Grasshopper, which are the data trees. Okay, so let's see how the data trees work. Now, when you see this fancy wire representation, it's not my word, it's just called like this in Grasshopper standard definition. So draw fancy wires means that we want to see the difference between different types of wires. So let's try to understand what different wires mean. When you have this single line cable here, it means that there is just one value passing through this wire here. So this wire is transmitting one single rectangle from the rectangle component to the populated D region input. Okay. When you see a 2 lines wire like this one, it means that there is a whole set of values running through this wire here. Now we must understand how this data here is sorted inside this group, and this is called a list. So let's see how a list looks like. I am taking just any of these components emitting a list. So here we are, and you see that a list looks like this. You have a let's call it the name of the list, which is this one, and you see it in curly brackets here on the top right corner, and this represents the group that contains all the values in our data set. Okay, and you see that the first value has index number 0, index number 1 is the second value, index number 2 is the third value, and so on. So let's say that we have 1316 points here. As the first point has index 0, the last point will have index 315. So if we scroll down to the bottom, you see that the last index is 315. Okay, but you see that meanwhile, while we are scrolling down or up, you see that there is no additional grouping, but the first one is 0, 0. So a list is one single group of values. Okay, so that's the way that we call this group of value a list. Okay, so what happens when we want to, and this group is basically acting like one single group when it reaches an input for any function that you want to use. So now let's say we want to use one single attractor point at a time. Okay, so we have the same problem because we have just one group with 2 items inside, and then this gets into the point A input together with point B from the populated to D, and then distance operates according to the longest list method. Okay. Okay, so if we want to consider these two attractor points separately, we cannot have them included in just one group. Okay, so we have to split them into two separate groups. And this is what the graphed tree component does, which is this one. Okay, so you can also call it like here in the command line, so graphed tree. Let's see what happens when I plug these points here in the graphed tree and then plug this graph tree into the panel. So you see that now the graph tree is doing its work, which is basically dividing or sending each of the points contained in the original list into one single group. Okay, so we have two groups, each one containing one single point. What happens if we do this and send this graphed tree into the point A instead of the original point component? So I do this graph tree and plug this cable here inside the point A. Okay, so now we have a different situation. Let me delete this panel here because cables or wires are crossing each other. So let me organize also the definition in order to have it more clearly understandable. So what we're doing here is grafting these 2 points here. And what happens inside the distance component? Let's see what happens here with a panel. You see that now we have distances here in this group, but if we scroll down, at some point towards the half, we see that there is a second group. Now, what's happening here? What is happening is that point A is getting 2 points, 2 attractor points separately. So it is calculating the distance between the first attractor point and all the population of points coming from the populated 2D. And then it switches to the second attractor point and recalculates all the distance between the second attractor point and the whole population of the 300 and whatever points. Okay, so this is outputting two sets of distances. You see that there are 2 branches here, 0, 0 and 0, 1, each one containing 316 values, which are the distances between first and second attractor point, which refer to the whole population of points. So distances are now referred to the attractor point. Okay, so they are calculated properly. And you see that when we graph the tree, we have this additional wire style. Okay, so remember that you must have draw fancy wires activated. It is activated by default, so do not ever turn it off, because if you turn it off, you have no differentiation between the wire types, and you don't understand what type of data structure is running through these wires. Okay, so keep this activated always. So this continuous cable is now indicating that there is a group of groups, basically. So a data tree, which is the one that we are seeing right here, is basically a list of lists, nothing more. Okay, so you have data grouped inside, but it's not just one group. There are several groups, each one containing its own set of data. Okay, so this is a data tree. And when you see this continuous cable, you know that there is a data tree structure flowing through this wire. Okay, so of course now we have 2 attractor points, so 2 sets of distances, and now we have 2 comparisons here, 2 evaluations. So you see that smaller than is also outputting its own data tree of true-false values. Okay, so you see that if we plug a panel here, you see that there is the first set of false, and somewhere you will have some trues, as you can see. And here you have the second set starting from here, and you have also some trues in this other set. So everything is working just fine. The problem is what happens inside this line here. Now this line is still connecting a list of 2 points with 2 different sets of points coming from the point cloud. Okay, now this dispatch, what is doing, we can also see what is the list A in this case. There is no advantage in plugging just inside a panel, because we only see these point coordinates here, but these are actually the points that are closer to each of one of the attractors. So you see there are 2 groups, because there is one set close to one attractor and the other set close to the other attractor. But if I take a point container and plug list A, now I can see that here we have the first set of point, which is basically closer to the first attractor point, and then there is the second set of point which is closer to the second attractor point. And so everything is working just fine here, okay, as regards the endpoints. The problem is that we have two separate sets of points here and one single set of attractor points. The attractor points are not separated in the start point. So what we need to do is the same thing that we did with the distance. So if we plug the same data tree coming from the graph tree here inside the start point, then we have the proper behavior for our double attractor structure here. And so you see that everything is working just fine. Okay, of course, the position is affecting the amount of points that we have inside each of the two sets here, but it doesn't matter basically. So we only we have the proper interaction between these two attractor points and the whole population of points coming from the populated 2D. Now, this is a more general definition with respect to the previous one, because this can also work with one singular point attractor. So if I set one point, you see that we are back to the original definition, okay, where we have just one attractor point and one spider moving around here. But if I decide to work with multiple points like 1, 2, 3, 4, 5, 6, we have 6 different spiders moving around in our definition. Okay, so this is a more general scenario for our point attractor definition, and you see that the only thing that we needed to do was to introduce this graph tree function. Now, this graph tree can also be made inside this point container. So if I copy paste this and I select right click and pick the option graphed, you see that this arrow pointing up appears in the component, which means that data inside this component are being grafted. Okay, and so you already see that this is telling us there are 6 values defined locally, but they are divided into 6 groups, each one containing one single value. And so each group contains one single point. While this one, without flatten, says I contain 6 locally defined value, but you see the list of coordinates, which means that you are seeing exactly the whole set of values inside this list. Okay, so when you see the values themselves, so it means you are seeing a list. When you see this representation here with indices in curly brackets and the amount of values inside parentheses, then you are looking at a data tree. Okay, and so if I take these 2 cables here, Control Shift and shift them to the new point container, then everything works just perfectly, and I can get rid of this old point container and graph tree. So this is the way that we build a point attractor definition with whatever amount of attractor points you might want to use, because they are grafted inside this point container. Okay, and of course we can also decrease or increase the amount of points in the point cloud in order to have a more saturated set of lines. Okay, so yeah, basically this is the theory behind the concentrated point attractor. I'm going to group it and turn it off by Control E. Okay, so now let's switch to the second type of concentrated attractor, which is the curve. Okay, I'm going to use the same initial set of random points, so I'm going to copy the rectangle and the populate 2D set of components. So we are back to this region with this population of points. And now I want to use a curve attractor, so I need a NURBS curve, which can be created starting from a set of points as vertices. And I'm going to set multiple points here. I want this curve to pass through our region like this. Okay, and I want to turn these points off, like preview off, and this is what we have for our attractor curve. So yeah, so basically the problem is absolutely the same. I want, for example, let's say that this is my attractor curve, and I want the points that are close enough to my attractor curve to be connected to the curve itself with perpendicular lines, okay, like this, like just creating a hairy line using this attractor theory. Okay, so this is what we want to do, and let's see how we can solve this problem, because now the problem is that we need to calculate, well, everything in the attractor theory is based on distance, okay, or mutual position. So in this case we must calculate the distance between each of the points of the populate 2D and the attractor curve. Now the problem is that the distance component that we have used only works between points, okay? So I cannot calculate the distance between points and a curve, because this component doesn't know how to handle this curve. It asks for points, you see the hexagonal icon, and I'm giving a curve, see the hexagonal icon, okay? So I cannot use the distance here. What I must do is calculate the distance between a point and a curve using the standard definition of this kind of distance. So say we have a curve like this and we have a point here. If we calculate the distance between this point and this line, the distance is defined like the smallest distance between this point and each of the points of this line. Okay, so in order to do this, we must consider the smallest distance, which is the perpendicular distance, okay, like this. And so it means that we must calculate the distance between this point and its projection onto the line that we are using. Okay, so if I project this point onto the line, which means basically project it perpendicularly to the line, then the point that results from this projection, it will be the one used to calculate the distance between the point and the line. Okay, so let's do this. The command that does this operation is called curve closest point, and it asks which points you want to project onto the curve, and I will give you the distance between the original point and the projected point. Okay, it's called curve closest point because when you do this kind of projection, the point of the curve that corresponds to the projection is the point of the curve closest to the original point. Okay, so that's why the name. So we project the point population onto the curve, and we have this kind of array of points, which are all the points of the point cloud projected onto the curve. But it doesn't matter, we don't want to work with these points here, we just want to work with the distances. So once we know the distances, we work exactly like before. We create a smaller than to evaluate these distances against a reference distance between 0, for example, and 20. And once we have the true-false set coming from smaller than, we just dispatch the population of points using this pattern here, and then we should have here the list A. Now let's take a look at list A, and list A is empty. You see the orange cable and also the empty set of values inside this panel. This is because our distance, our reference distance is set to 0. So there is no point in the point cloud that is closer than 0 to the attractor curve. So if I increase this, you see that points start to appear in our list A set. Okay, so we have the points. We can also display them by using a point container, and you see that these are the closest points to the attractor. It depends on how high is the value of this reference distance. Okay, so what I want to do now is connect these points to the line in order to create this kind of hairy line here. Basically, connecting this point to the curve means that we want to create a line between this point and the projected point. But we already have the projected points, which are these. But we cannot connect the points that satisfy this condition here, like point A, start point, with all the points coming from the curve closest point, because the curve closest point is projecting the whole cloud of points. So we have here 173 projections, while in this container we only have the 31 points which are close enough to the attractor curve. So we are comparing, or we are making creating the interaction between 31 values and 173 values. Remember that Grasshopper uses the longest list method, so we have 173 lines coming out from this component here, but they are connecting the points like randomly and without any meaning, okay? So we need to understand which of these projections here corresponds to the same points that are close enough to the attractor curve, okay? Now, somebody would say, well, you should calculate once again the curve closest point, project this new set of points onto the same attractor curve, and so you have the points that are close enough to the attractor and only their projections, so you can create the line between these points here and their projection. And everything is working just fine, okay? But I prefer to give you another idea of how to solve this problem because I want to let's say fix this comparison here and selection with the dispatch once again. So let's say that, for example, we have the population of point and we came out with a true-false pattern that is basically selecting with list A only the points that are close enough. What I want to point out is that in Grasshopper, the order of data inside a dataset never changes unless we want it to change. So let's say that we have the population here, okay, and then we project the points onto the curve. The way that these points, for example, are sorted inside the curve closest point corresponds to the same order, the same sorting of the distances. So, for example, first distance that we see here corresponds to the first point of this population and also to the first projection of this point onto the attractor. Okay, so what does this mean? It means that if the first distance is giving us a false because the point is too far from the attractor, then also its projection, the first point in this projected list corresponds to the same point which is far from the attractor. So it means that when smaller than says true, it refers not only to the distance but also to the point that is close enough to the attractor, and also its projection occupies the same position in the list as the true value in this smaller than. So if we take the dispatch and copy paste it and use the same dispatch pattern to dispatch the projections, then in list A we will have 31 projections that are basically just the projections of the points that satisfy this smaller than condition. So if we take a line and plug list A and list A, then we have the lines connecting the closest point. Of course, we can also use list B and list B, and we are creating longer hair because we are connecting the farthest point to the attractor, okay? But we want to create this using the smaller than. And so we consider the points that are closer to the attractor. And you see that only those points are being connected to the attractor curve, okay? So it's basically, as you can see, it's absolutely the same workflow as for the attractor point. The only difference is that we needed to switch from distance component, because it only works with two sets of points, to the curve closest point components that projects points onto the curve and calculates the distance, okay? And also keep in mind that we were using two dispatch functions here because Grasshopper doesn't change the order of data inside data sets unless we want it to change, okay? So that's why we can use the same pattern to dispatch different sets of values here. Now, just because we did it with the attractor points, let's see what happens if we want to work with a couple of attractor curves, okay? So what I'm going to do right now is take, of course, if I turn the preview on, you can see that I can also change things in real time here by moving around the vertices of our control point curve, okay? So if I take these two and copy paste them, and say I want to create a different attractor, so like moving these points around here and creating this new curve, I don't care what this curve does outside from our region, so I will just move it here towards the lower left corner of our region. So here it is. Okay, so I want these two curves here to work as two attractors. Okay, so what I'm going to do right now, I'm going to plug this here, and you see that things apparently look fine, but if we move around the first attractor curve, we might find something weird. I don't see it. I don't know where it is, but what happens here is that we have the same exactly the same problem. We are not considering the two attractors like separately, we are considering them all together. Okay, and so this causes just one attractor to function in the proper way inside our definition. So once again, what we can do is graft these curves here, and now you see that everything works just fine because points are projected twice, once on one attractor and the second time on the other attractor, and then we have two patterns of smaller than, and then we are dispatching the points, original points, and also the projected points, so we only have the lines connecting the right points, the closest points to each one of the attractor. Okay, so you see that once again the solution is using a data tree. Just because we are seeing something that starts to make sense in order of having some design possibilities in our workflow, let's not use some random NURBS curve like these two here without any design meaning basically, and say I want to use some circles. Okay, so what I want to do, I want to set multiple circles right now, and I want to use one small circle here and another small another circle like this. Okay, so if I plug this here and turn on the lines here, you see that now we have these two sets of lines. We can decrease the reference distance for our attraction here. So if I turn off everything but our lines, you see that now we are starting to get some kind of interesting design from this definition. So remember that, well, actually you can work like in an experimental way, but I do prefer to take everything that we do in this course and bring it to some design solution. Okay, so you see we have some kind of crowns here of lines around the two attractors. Okay, and of course we can also create some kind of selection here. I call it a switch. So let's see how it works. Basically I want to switch between two different sets of input, like these two lines here and this circle container. So in order to switch between the two sets in the quickest way possible, I normally create a switch. So the curve is asking for a curve parameter. So I take a curve parameter and plug it here. Okay, of course now it is empty, so the curve closest point is not receiving any data, and anything on the right stops working. Okay, so it says I'm not receiving data, I'm not receiving values, I'm not receiving values, I'm not receiving values, because this is empty. Okay, so what we must do here is create a switch. Now it's very easy to plug the circles here and everything goes back to normal. Okay, but it's not easy to plug each of the two attractor curves like this. We must shift, drag a new wire in the same component. Okay, by the way, you see that some things I keep it like inside the workflow without giving them too much importance. But if you want to plug two wires inside one single component, you just shift and drag the second wire, and then you see that the two coexist in the same input. If you don't press shift, the second wire will substitute the original one. Okay, so by the way, we must plug two wires here. But if we take another curve container and plug the two wires here just once, now we have a switch. Okay, so if I plug this, I have the circles. If I plug this, I have the two attractor. Okay, normally what I do, I keep everything off, but the curve container. If I want to see what attractor I'm using, I just keep this with a preview on, and then I plug the wire that I want to plug. Okay, and normally what I do in order to recognize that there is some selection going on here, I select these 3 things or 4 or whatever if I have several sets of attractors, like in this case, and group them, and then right click on the group and change the color to a 50 yellow with saturation and alpha. So here this means to me that I have to make a selection in this area, and you see that I only have the 3 components that determine this switch. Okay, so this is good for the workflow, because it is clear what's the intention in this yellow group. Okay, so just if you want to share this organization with definition organization with me, you're more than welcome. I find it very useful. But anyway, so this is the concentrated attractors curve with the more general definition that can work with any amount of attractor of any shape. Okay, so once again, let's group this and disable this with Control E. So let's say that this is 1A and this is 1B, because we are referring to concentrated attractors. Now let's see what we can do with this. Let's play around with them. Okay, so one exercise that always fascinated me when I was learning Grasshopper almost 20 years ago, basically, is based on point attractors. Okay, so what I'm going to do right now, I'm going to take this set of components here, not the whole group, I don't care about the whole group, I Control-C, Control-V them and turn them on. So I have this this rectangle here with the populate 2D and so on. I'm going to stretch the rectangle vertically a little and horizontally a little less, like this, a vertical rectangle with a bunch of points like this. And I don't want to see the rectangle anymore, I don't want to see the populate 2D anymore, and I don't want to see the dispatch because it's the same set of points. And I want to work only with 3 attractor points, like set multiple points with 1 here, 1 here, and 1 here. Okay, and I don't want to create lines. Okay, I don't want to create lines. I just want the attractor point to define some kind of interaction. But what I want to do right now is, you see that we have 3 sets of points here, and this is because we are using the dispatch. Okay, but what I want to do right now, I don't want to dispatch things. I want this definition to affect the whole population of points. More specifically, what I want to do is create circles using the populate the whole population of points, but I want this circle's radius to be affected by the 3 attractors. Okay, so let's say that we have the distances calculated here. You see that there are 3 sets of distances, and therefore I don't need this reference distance, nor the smaller than, nor the dispatch. I don't need anything of this. Okay, so what I want to do right now is just affect or determine the radius of these circles based on the distances between the 3 attractors and the point cloud. So what I'm going to do is this. We have 3 sets of distances here. Pay attention to this thing, because we are going to see one important component in data tree manipulation in Grasshopper, and it is a component that is used in several occasions. Okay, so you see that there are 3 groups. Oh, by the way, I told you at the beginning of this course that we were going to use an important component, which is the param viewer. Okay, so this is the first time that we use it, and I'm going to show you how it works. You see that the param viewer only shows the structure of the data inside this data set. So it is telling us that there is a data structure with 3 branches. These are the names of the branches, which are basically the names of the lists, And this is telling us how many values are inside each branch or each list. So 265, 265, 265. Why? Because we have 265 points coming out from the population, and we are measuring the distance 3 times each per each attractor. Okay, so this is what happens with this distance. So it's giving us a data tree with 3 branches. The param viewer also has a different visualization style. If you double click on it, you see that there is this graphic representation of the data structure, and you can also see clearly why we are talking about data trees. You see that there are branches graphically represented like in this way. But I find this representation, well, almost useless instead of this one. This one is the useful visualization of a data tree, because you have all the information regarding the data tree itself. So I do recommend that you use the param viewer like with this representation here. So once we know what's the data structure inside this distance output, we also know that the distances here are grouped by attractor point. So basically the distances, the 265 distances here refers to the first attractor point, and then this 265 to the second, and this 265 to the third one. So if we take these distances here and use them as radius, what we are getting here are basically, you can see it with another param viewer, we are getting 265 circles per attractor. So each point of the point cloud is generating 3 circles, and their radius is actually the distance between each of the 3 attractor points. Okay, so this is what's happening, and you see that all the circles pass through each one of the attractor point. Okay, so that's why you see these circles converging inside this attractor point here. And if I select this, you see that this is the attractor point, and also this one, and also this one. Okay, so this is what's happening. Now, I don't want to do this. I don't want to use 3 radiuses per each point of the point cloud, because I just want to affect these circles here, which are referred to the point cloud and not to the attractor. So what I must do is basically provide this component here 1 single radius per plane or per population point. And so I must derive this radius from the combination of the 3 distances that I get from the 3 attractors. Okay, so somehow I must combine the 3 distances that refer to the same point of the population and not to the same attractor. So what we have here, let's grab the param viewer again and let's see what happens with this process that we are creating. So what happens here? We have this data tree with 3 branches, each containing 265 values here. And what I want to do is refer 3 distances to each of the 265 points of the population. So basically what I will get are 265 branches. Each one will contain 3 distances. So if I refer, let's make a quick scheme here. If I have one attractor, and then point all around, okay? If I consider this point here, I will have 3 distances referring to the 3 attractors, okay? If I consider the attractor point, I will have 265 distances, because I will consider these distances between him and all the population, okay? So if I invert the situation, I will have 3 distances per point of the population. So inverting, it's in Grasshopper, in this case, inverting this data structure is called flip matrix. So it's just a small function here, but it's very important, because if I do this, what I get as a result is this thing. Is a data tree with 265 branches, each one containing 3 values, which are the 3 distances referred to each point of the population. Okay, so this is what we are doing here. Now, if besides the param viewer, which gives us an idea of how data are organized inside a data set, it's important to understand what happens with the values, okay? So you see that we have 3 values per each point of the population. And this, for example, means that this point here, the first point of the population is closer to the third attractor. As you can see, its third distance, it's 11, okay? So that's the meaning of these 3 values here. Now, if we want the radius to depend on all 3 values at one time, what we can do is basically, let's say, well, combine these values together. So one thing that we can do is create an addition of these 3 values and see what happens initially. Of course, it won't be the right solution, but it's a beginning, okay? So let's say that we want to create an addition or a plus. So if we take this plus component here, the problem is that, well, this is a dynamic component. So if we get closer, we can also add a third input, as you can see. But all our distances come from one single data tree. So I cannot plug these, and these, because what I will do is basically create an addition between this group of values and the same group of values and the same group of values 3 times. Okay, so if I do this, as a result, I get once again a data tree with 3 values per group, but these values here are the 3 times the original value coming in from the original data tree. So 205 is 3 times this value here, okay, because I am making twice the same addition. So I cannot do this, okay, and in order for this to work, I should use another component here in order to have this value here in a separate branch, this value here in a separate branch, and this value here in a separate branch. Okay, so I can do this, but I prefer not to in this moment. If we want to perform the addition of several values coming from the same input, we can also use this other component, which is called mass addition. So the mass addition only asks for 1 input, okay, and it basically adds together all the values that are grouped together. So in this case, for example, the mass addition input, what is receiving in the input parameter is this data tree. Now, it can only perform the mass addition in data that are grouped together. So it will perform the addition between these 3 values here, and it will give us a result, and then it will get the second group and perform the addition of these 3, and then these 3, and so on. Okay, so each group will convert from the 3 distances here to the sum of the 3 distances altogether. So if I copy paste this panel here and plug the result, you see that this is 122, which is exactly the result of the addition of these 3 values, and 129, and so on. Okay, so here we have 1 value per each point of the population. So 265 values of the coming from the distance, and here we have 265 points coming from the population. Okay, so one might think, okay, so let's plug these results to the radius. Well, before doing this, I'm going to reduce the amount of points, because this is going to be something that could crash Grasshopper. Don't do this, because if you do this, what is happening right now is that we are not getting, for example, I have now 45 points here, but I am getting 2025 circles. Why? Because we have one single list of centers and a data tree of radiuses. So what happens here is that, well, let's take a look at this with another panel. So I have this population of points, which are 45, and these are the radiuses. Okay, so what happens here is that we have just one group of centers, which is this one, and we have separate groups of radiuses. Okay, so what happens inside the circle component right now is that all these points generate one circle using this radius, And then all these points generate another circle using this radius, and then this one, and then this one. Okay, so we have 45 points using 45 different radius each. And then we have 45 by 45 circles coming out from the circle component. Okay, so this is what happens. So in order for this circle to work properly, if we want to keep radiuses separated, then we must also separate the centers instead of having them grouped together in just one list. So we can either graft the centers, or we can flatten, which is the opposite of grafting. Okay, so let's take a look at this second solution. So we introduce also the flattened tree. If I flatten tree something, you see that, for example, let me get rid of the list of points. So you see, for example, this is a data tree of the addition of the distances. If I flatten this and then I plug the result into another panel, you see that these are the same values but flattened inside one single group of values. Okay, so this is the opposite of grafting. So I can also flatten the radiuses here and get 45 circles right now, each one using one center point and one value for the radius. Okay, let's get rid of these panels here now that we know how things work. And also let's get rid of param viewers. I normally use them but then delete them when I no longer need to understand what data structure I'm working with. Okay, so here's the definition that creates circles starting from the attractor point. Okay, of course you might observe that if I move these, I am changing the radius of these points, and it's quite evident that if these 3 points get closer and closer, this circle starts to become smaller and smaller because their radius depends on the addition between the distances from each point of the point cloud and the 3 attractors. Okay, but these circles have quite a huge radius. So what I want to do right now is take these values here and scale them down somehow. So in order to do this, what I'm going to do, I'm going to shift the flatten from this input to this output. It's not important when you let's say apply the flatten method here, as long as this component receives a list. So either you pass a list with a wire, or you convert a data tree into a list using the flatten option inside the input. It doesn't matter. But as I want to perform some kind of operation on this set of values, I prefer to shift to the flatten in this result output here. And so, as you can imagine, we have just one list of values here, of numbers. So let's see what we can do with this. And let's see that these circles are too big. So first try should be to divide, for example, the result of this mass addition by a number. So if I take a number like a 11 slider and set it to, well, not 0, just 1, and then use this as radius, nothing changes because I'm dividing by 1. But if I increase this, then the radius starts to decrease. Okay, and you see that circle starts to be small enough to fit inside this area. So now that we have flattened and the circle is receiving the proper amount of planes and radiuses, I can also increase the amount of points. Okay, so we have a clearer idea of what will happen, like in this case. So this is a very, very basic manipulation. If I see that a value is too big, I can divide it by a coefficient and then have a smaller set of values that might fit in our geometry. Okay, but as you can see, this is something quite, let's say, simple in terms of design. You see that, well, if you don't see it, I will point it out. You see that we have the 3 attractor points like in this area. All the circles that are inside this area will have a smaller radius, and all the circles that start to get far from this triangle, they become larger. Okay, this is quite normal according to our structure, our design. Okay, so it's a very basic condition. It has no let's say no particular meaning in terms of design. But what we can do is like converting this like a pond where we throw 3 stones. Okay, so let's imagine, for example, that I have a rectangular pond with water inside, and then I throw a stone here, and a stone here, and a stone here. Then this stone generate a set of waves like this. Okay, that gets farther and farther and farther. But also this one will generate its set of waves that gets farther and farther and farther. And also this one. Okay, like this, and like this, and like this, and like this. Okay? So what I want to do, I want the interference between these 3 sets of waves to determine the radius of our circles. And this thing will be more interesting than the simply dividing the values by a coefficient like this in this case. Okay, so let's keep this scheme here in order to remember what we want to achieve, and let's see what we can do with these distances. Now, this is going to be another a very important workflow, because this is something that you might want to fix in your memory, because you are going to use it several times in your life. Okay, so I'm getting rid of the division here, and let's make some considerations for these distances. Okay, let's go back to our distance, and what I want to do, I want to simplify this definition just working with one single attractor point, like a stone thrown in the center of the pond. Okay, so let's take a look at what happens with the distance in this case. We have these values here, which are sorted randomly because the points are being generated randomly. So remember that populates are functions that generate pseudo-random set of points depending on a region, or a 3-dimensional region, or a geometry. We will talk about that this later. So these distances here are sorted randomly, but the thing with the distance, it might sound stupid, but the thing with the distance is that it grows with the distance. Okay, so for example, if I have the attractor here, and then I have a set of points here, like this, and I calculate the distance between these, as I move away from the attractor, the distance is getting larger and larger. Okay, so if we want to consider, for example, an effect like the ripples on the surface of a pond caused by the stone, then we must come out with some values that, while the distance increases, the values start to oscillate like this. This will be the peak of our waves, then we have the valleys, then we have the frequency. So we are talking about waves in the proper way. Okay, and there is one function that has this periodic behavior, which is very well known, which is called the sinus, or the sine function. Okay, so what we're going to do right now, we are going to convert the distances into the input for a sine function. In Grasshopper, we can work with the function in 2 different ways. If you want to perform some kind of, let's say, complex operation, I do recommend that you use the math toolbar, where you will find the several ways of defining functions. You have polynomials, which are some very simple functions, or you can use the script group of commands, especially the expression one, where you can also create your own functions here, accessing a whole set of functions here in this library here. But we will talk about this later, because we will have the occasion of using complex functions. Inside this math group, there is also trigonometry. Okay, so you will find the sine and cosine function like this, and they ask for input values, and they just give you the result. But there is another way of working with functions in Grasshopper, which is using the graph mapper. Now the graph mapper is, you can find it in the params and input graph mapper. Here it is. Okay, the graph mapper is basically a converter of values, and it converts a set of values into a new set by using the graph of a function, of a given function. So once you place the graph mapper inside your canvas, you might want to select with the right click what graph type you want to use. And in our case, we want a periodic function like the sine. Okay, so you see that now we have this wavy aspect of this function. You have handles here. You can select how many waves you want to consider for your functions and so on. Okay, but let's leave it like this for now. So what I want to do, I want to convert the distances into this periodic behavior. Okay, and the way to do this is like this. I'm going to sketch it in order to be more clear. So let's say that this is the attractor point, and this is the growing distance. So we have the point cloud, and our distances are basically all aligned along the distance axis. Okay. So what happens is that when we use a periodic function like the sine starts to do like this. In our case, it doesn't become negative, and we will explain this in a minute. So when the distance increases, this means that the sine will have a specific value calculated on the output axis. Okay. So when the distance keeps on increasing, the values of the sine of the distance can also decrease and then increase back and then decrease back and so on. Okay, so as the distance grows, the sine of the distance goes up and down in a periodic way. Okay, which is exactly what we want in order to affect the radius of the circles, like with ripples. Okay, so we must take these distances and plug them into the graph mapper, but there is one problem. If we take a look at the output here, we have some periodic behavior, but it is not as expected. Okay, why? Because the graph mapper is telling us in its graphic that I only accept values between 0 and 1 as independent variable, like in the distance axis, and I will give you back values between 0 and 1 as the output. Okay, so it is giving us values between 0 and 1 as the output, but it is not receiving values between 0 and 1 as the x variable, let's say so, because we are passing values like 33, 39, 20, 14. Okay, so they are all values larger than the range of values that it is expecting, like this, like in this moment. Okay, so it is working properly actually, but it's like if we are considering, this is the attractor, we are considering distances between 0 and 1 in this, for this function, and we are giving values like here. So what happens in this interval like this is that the sine grows up and then it starts to fall down, grows up, falls down, but we are not controlling what happens in this area. We just control what happens inside this one. Okay, so if we want to have this graph mapper working properly, we can do two things. First one is double click on the graph mapper and extend the x range for the input values. Now this is something that I do not recommend, never, because we can do this of course, but in order to do this we must know what is the highest value of the distance in this moment. So we must perform an analysis of this in order to know what is the x1 value that we can set inside this value here. Okay, but I do not recommend it, because if I take this point and move it away like this, the range of the distance coming out from this component is changing, and so I should manually change once again this value inside the graph editor in order for this graph mapper to work properly. So I do not recommend to do this never edit the ranges of the graph editor, of the graph mapper. Okay, always work with a normalized graph mapper, so 0, 1 and 0, 1 horizontally and vertically, and do something in order to convert the values in the range 0, 1 before entering the graph mapper. Okay, so how can we do this? Well, it's like having a set of distances ranging between, I don't know, 5 and 50, and wanting them in a new range between 0 and 1. So the work that we are going to do is convert this range here into the new one by converting 5 into 0, 50 into 1, and all the values in between will be converted into the correspondent values in the new set from 0 to 1. So it's like shrinking the domain 5 to 15 to the new domain, to new range 0 to 1. So you see, we are starting to talk about domains, which are basically a range of values. Okay, so this operation here can be done using the remap numbers component. And this does exactly what I was writing here in the sketch. So it asks for the values that I want to remap, which are all the distances, and it asks for the source. Now the source is the actual range of the distances, and so the range is basically an interval of values ranging from the smaller distance and the larger distance in our case. Of course, we won't determine these two values by hand. There is a component which is called bounds. Now the bounds takes a set of numbers and tells what is the range that includes all the incoming values. And you see that the range is 1.57 to 72.60. Okay, so this is the actual range for our distances, and these will be plugged into the source for our remap numbers. Okay, and now it asks, what is the target interval that you want to use? And it says, I give you one default domain, which is from 0 to 1, which is just perfect because the graph mapper needs values between 0 and 1. So let's see what happens with these two panels here when I plug the distances here and the mapped values here. So in the range between 1.57 and 72, the first point has a distance of 57.85 more or less. But the same point in the range 0 to 1 has a distance of 0.79. So you see that 0.79 is close to 1 because the distance 57.84 is closer to 72, which is the extreme, the upper extreme of our source domain. Okay, so everything is working perfectly. When the value is closer to the initial value of the range, like in this case 12 is closer to 1.57, you would see that the mapped value of the distance will be a number which is closer to 0. Okay, so when the value is 38, which is in between 1.57 and 72, then we see that the mapped value will be more or less 0.5. So everything is working properly right now, and I will plug the mapped value inside the graph mapper. And so you will see now that the values of the distances will all be aligned along this axis. So I expect my values here to basically oscillate between 0 and 1 like this. Now they are randomly sorted, so you don't see let's say a growing value and a decreasing value, but these values here are being converted using the sine function. Okay, so you can see that now all the values are affected and everything starts to work just fine. Let's see what happens if I plug this here into the radius. So now you see that the points that lie closer to the attractor point are receiving a radius of 0 basically, and as the distance increases, the radius of the circles increases as well. And if I take this function here and change its periodicity like this, you see that now at the maximum distance we are getting another time radius of 0. But if I do like this, I will have this wavy behavior for our circles. Okay, So this is what happens with just one attractor point. Okay, now what happens if I right click here, select multiple points and pick 1 and 2 and enter? You see that things start to work just in a weird way because we have 2 circles per each point of the population. And why is this? Because we are still working with radiuses that are grouped by attractor point. So once again, we must use the flip matrix. And now I have 2 periodic functions here, or 2 periodic sets of values coming from the graph mapper. And what I will do is flip matrix them in order to have a couple of values per each point of the point cloud. You see that 0, 0 contains 2 values, 0, 1, 2 values, and so on. I must addition these values here, which are the remapped and graph mapped distances, in order to have just one value for our radiuses, and then I plug this into radius. And so we start to have some kind of interferences between these 2 points here. So you see that this is one ripple generated by the first attractor, this is one ripple generated by the second attractor, but you also see that there is this set here, which is caused by the interference of 2 ripples, and also here. Okay, so if we start to create this kind of interferences like this, things start to look quite interesting. And of course, we can also work with the amount of points that we want. We can also use the original 3 points that we were using. And I can also reduce the size of the circles by reducing this peak here for our function. And you see that now we have this kind of interferences between the waves in our population of points. I can also increase the amount of points for our population in order to see the waves more clearly. As you can see, we start to see circular pattern for our waves, okay, like this. And we start to have interferences coming out from our set of attractors, okay, which is more interesting than what we were doing before. And this becomes also evident if I try to move one of these. You see that there is a whole circle or concentric circles of waves that are being determined by this point here. And of course, what we can do, moreover, is to differentiate the frequency, or basically the frequency of this wave function per attractor. Okay, so for example, how can we do this? Well, actually, in order to do this, we should separate the values that we are using here. So for example, let's say that I want to remap. In this case, what I am remapping right now, if you consider this function here, we have 782 distances per each attractor. Okay, we can also flip the metric before using the graph mapper. Okay, so instead of having all these values grouped by attractor, I can already have the values grouped by point, by a point of the point cloud. Okay, so let's see what happens if I switch this flipping here. I flip matrix these values here. Okay, and then I am going to use this tree here in order to perform this kind of operation. I'm going to use one graph mapper per each attractor point. Okay, so this is what I'm going to use. And in order to do this, I must remap using the graph mapper the 3 values contained inside each branch of this data tree independently from each other. So I need, for example, you see that we have 3 values per branch. I need the first of these 3 values to be affected by this graph mapper, the second by this, and the third by this. So I need to separate the 3 values instead of having them coming out from one single wire here. And in order to do this, I'm going to use a component which is called list item, which is this one. Now the list item takes a list and it extracts only the item corresponding to the index that I want to consider. Now in this case the index has a value of 0. Okay. If we take a look at the values inside this data tree here, you see that there are several lists. Each one contains 3 values, and these 3 values are called 0, 1, and 2. These are the indices. Okay. So when I say list item, consider this data tree here and extract only the values with index 0, he will extract the index 0 of the first branch, the index 0 of the second branch, index 0 of the third branch, and so on. So these here will be just the first values of the distances. So all the first distances will be here put inside this list item. Okay, but I also need to extract the second value and the third value. Okay, so index number 1 and index number 2 per each branch. So I get closer to this, I add the +1 and +2. So basically what we have here, let me move these things away a little. So we have the original data set like here, and if I take another panel and see what happens here in the first output, I have 0.21, 0.95, 0.49, which are the first value, 21, 95, 49. Okay, if I plug the +1, I will have 63, 68, 58. You see 63, 68, 58, and in the +2 I have 84, 26, 39, which are the third distances in our group. Okay, I moved down too much. This is 39, as you can see. Okay, so we have the 3 values here, and I want to use them each with its own graph mapper. Okay, so this is what I'm doing right now. I'm going to move this a little down like this. So now we have 3 distances being affected by 3 separate graph mapper. And then what I want to do, I want to take these 3 values and add or perform the same mass addition that we were doing before. So I don't need the flipper matrix anymore here because we did it here. And so what I'm going to do right now, these are the output of this graph mapper are numbers. As you can see, these are floating point numbers. So I can take a number container like this, plug all these 3 wires like here, and you can see that we are reconstructing the set of 3 values as before the list item. Okay, we will discuss this later eventually, why this is working like this. But anyway, nevertheless, we have 3 values here. We can mass add like this, and we have once again our circle behaving exactly like before, but we have 3 different functions. So if I want a stone to have ripples which have a higher frequency like this, I can set it using this graph mapper, and these affect the second attractor, and these affect the third attractor. Okay, so now I have 3 different attractors with 3 different weight or frequencies for their interaction. And also, if I see that this result here is too high, because I am getting circles that starts to overlap too much in this case, I can do another thing. I can remap once again these values using their original source domain, calculated using the bounds, and once again use the 0 to 1 target domain for now, in order to have smaller circles which can be nicer to look at. But I can also define the target domain. So I still see that 1 is too high for the density of points that I have in my population. Let's say that I want to work with even more points in order to have a clearer view of these interferences here. And then what I'm going to do, I'm going to use another remap number where the target domain, instead of being 0 to 1, I want it to be from 0 to a smaller value. And I can create a target domain by simply plugging here the highest value of the range. And so I will take a slider, or I can also take a natural slider like this one and plug it here. So what I'm saying here is that the highest value is 0.25, so the target domain will be from 0 to 0.25. And I start to see that I can also adjust the size of the largest circles here, thus creating this kind of nicer aspect for our ripples. Normally, when you throw a stone inside a pond, even if the frequency is actually constant, but the intensity of the waves decrease according to the distance. So it's proportional to the distance, but it's inversely proportional to the distance. So in this case, instead of using simply a sine function, we can also use a sine c, which is a function that decreases with time. A sine function that decreases with time. So if I take this and get closer to the origin of the graph, you see that the amplitude of this wave is decreasing. Okay, and if I do this also with the other functions, like using sine c, always with the, well, it can be the peak or the valley with corresponds to the attractor. It depends on you. And I want to use, for example, like a shorter period, and I want this to have a sine c with, let's say, a lower effect on this ripple. So now you see that we are starting to get some nice behavior for our ripple generator. Okay, and you can see that we have a very nice design coming from these points here, with interferences and so on. So as you can see, working with attractor is not, let's say, by itself is not that interesting maybe, but if you start playing with them, you can create some interesting, behavior. Like, for example, in this case. Yep, okay, nice. Of course, there is one problem with this definition in this moment, and the problem is this. Everything works just fine in this moment, but if I right click on this point container and set multiple points and pick 1 and 2 points, I have something weird happening, because this list item is extracting 3 values from a list that only has 2 values. Okay, so what happens here is that the first value is correctly 0.77, as you can see is this one. The second value should be 0.74, and here you have it. And the third value, who is the third value, is once again 0.77. Okay, so the problem in this case is that we are adding twice the same value belonging to the second attractor point. The first attractor point. So this is altering the result, the design result that we are getting. So the problem is that we cannot parametrically connect this part of the definition to the amount of points that we are using here. Okay, so this is something that we cannot do. So this definition only works if we consider the proper set of attractor point and the proper set of graph mappers that we are using here. Okay, so there is no way for this definition to accept whatever amount of attractor point that you might want to use in this container. Okay, so if you want to have a definition that can work with any amount of attractor point, then you cannot differentiate the wave basically with 3 separate graph mapper. You must switch back to the previous solution. I will just repeat it here. I will take the graph mapper, take the sine function, and then affect all the values here with the same sine function, and then take these values here, and now everything is affected by the same sine, and so we have this kind of interferences like here. Okay, but if you want, and this will work with the amount of attractor that you please. So if you set 1 point, you will have just 1. If you set multiple points like 2, you will have these 2 here, and so on. You can also draw with this definition, and it's very interesting to draw with this oh well, let me group this, because this is a particular solution that I'm not going to consider right now because it is not parametrically connected to our workflow. So remember that the ideal workflow is always entirely parametrically connected. Okay, so you don't have to do anything by hand once you have developed the first solution. Okay, so this is our goal basically. So let's say that we have this definition here working properly with just one function affecting all the distances. How can we design with this? Well, for example, we could take the attractor point and give them some rational position, not just picking them randomly inside our region. Okay, so for example, let's say that I want to create a circle, and I want to create a set of points along this circle, and I want the waves to be originated starting from these points here. Okay, so distributed evenly along a circular curve. Okay, so how do we do that? I'm going to create a circle and set one circle and place it like here at the center of our pond, and now I need points along this curve. And in order to create points along a curve, well, in Rhino you have the divide curve by number of segments, and in Grasshopper you have the divide curve command. There is also a divide curve by length, but anyway, we need the divide curve right now. So if I do this, I am dividing the curve, the circle, into 10 parts. Okay, and then I'm getting 10 points. So if I plug these points here in the point container, now these points are the origins for our ripples. Okay, now if the amount of points is 10, the combined action of all these waves generator, basically the interference is creating one single macro wave here all around the circular area. But if I decrease the count, for example, like taking a 5 slider, if I decrease this, I give space between the attractor in order for these interferences to be present also at this point. And I start to have this kind of nice interferences here. If I reduce it a little more, I also have a more evident behavior. Okay, but with 5, we can also increase this, and we can see, for example, what's the final result like this. Okay, yeah, basically this could also, this starts to be an interesting design pattern inside our region. Okay, so as you can see, attractors and curve attractors and point attractors can be very interesting to work with due to this kind of considerations. Okay, so just I invite you to play with these definitions here. I will share them, of course, in the description of these videos, so you will have them available and you can experiment with them, because that's the more interesting part. Okay, so once again, I'm going to group and disable this part of the definition, and I'm going to place it like here, because this is something that has to deal with our main group, which is the concentrated attractors. Okay, so now next step is to discuss the diffused attractor, and this is going to give us access to a whole set of operations that are normally used also in production, both in architecture and in design workflows.